Freight trains weighing thousands of tons carry massive amounts of kinetic energy. When moving that much mass at speed, the margin for error is zero. Operating a national network presents a logistical problem. No two stations are physically identical. They have different track layouts, varying gradients, and a mix of century-old legacy hardware operating alongside modern digital systems. This geographic and mechanical diversity makes it impossible to write a single set of physical safety rules that applies everywhere. What works on a flat, straight track in a valley could cause a derailment on a steep, curved mountain pass. To prevent accidents, engineers do not try to standardize the physical tracks. Instead, they standardize the procedural logic applied to those tracks. Railway safety emerges from an invisible, highly localized algorithm of operational law. In Malaysia, the National Railway Operator, KTMB, relies on a specific administrative framework to enforce this localized safety. The foundational document of this framework is the Perintah Kerja Station, or the Station Working Order. The Station Working Order, or PKS, acts as the absolute local law for a specific station. It overrides generalized assumptions a train driver might have about the network directly onto the unique signaling hardware and block systems installed at that exact geographic location. This document serves as the essential translation layer. It takes high-level routing commands from central dispatch and converts them into safe, physical ground movements. Without a validated PKS, a station remains inoperable, lacking the core logic required to prevent disaster. Operational rules must adapt whenever a station's physical layout or signaling hardware undergoes maintenance or upgrades. The first phase of this adaptation is drafting a sementara, or temporary, station working order. This flowchart outlines the strict workflow to deploy temporary local law, beginning with managers drafting the order before a new layout is commissioned. Once approved by the regional manager, this draft has a strict temporal boundary. It is legally valid for exactly 3 months. This 3-month window functions as a live fire beta test, forcing operators to prove the localized safety logic under real-world conditions before it becomes permanent. To transition the order to tetap, or permanent, the system undergoes another rigorous bureaucratic cycle. Making the rules permanent requires high-level executive certification. The general manager of operations must formally sign off before the permanent order is distributed to the station to be enforced. In rail engineering, administrative bureaucracy is deployed as a strict safety filter to prevent untested procedures from going live. Once the PKS is approved, it dictates the specific data and protocols required to control the yard. Section 3 of the document establishes the technical baseline of the station. Items 3.3 and 3.4 explicitly document the local signaling infrastructure, dictating whether the signals are mechanical or electrical and how the physical semaphore blades operate. Defining the hardware is only the first step. The PKS must then dictate exactly how trains interact with that hardware. Section 11, Arahan Lanceron, controls the most dangerous operational edge case in a rail yard, shunting. Shunting is the localized moving and sorting of rolling stock from one track to another. This risky process often requires moving against standard mainline flow. The PKS acts as a modular blueprint, dictating exactly which maneuvers are permissible within the station's unique geometry. Shunting often requires a train to intentionally move past a signal locked in the stop or danger state. To authorize this safely, the PKS relies on specific visual heuristic that translate abstract rules into physical instructions. These instructions change depending on the time of day. During the day, the visual authorization for forward shunting is a mechanical semaphore blade lowering to an angle between 45 and 60 degrees. At night, those mechanical blade angles are invisible. This introduces a critical failure point that requires a complete translation of the authorization protocol. The rulebook dictates an electrical equivalent for nighttime. The authorization translates into a single green light or 2 distinct white lights positioned at a precise 45-degree angle. Regardless of the visual medium used, the operational meaning is identical. Move forward with caution, only as far as the line is clear. These strict daytime and nighttime visual rules prevent driver misinterpretation when navigating a restricted yard. Environmental variables force safety systems to be fluent in multiple, highly specific visual languages to maintain authorization. Flawless hardware and visual signals mean nothing if the human operators on the ground act unpredictably. The baseline environmental rule for any station is an absolute prohibition of trackside presence unless it is operationally critical. If a worker must be near the tracks, Rule 3.4.1 mandates they hold the KTMB 0. Furthermore, Rule 3.5 requires that upon hearing a train's warning signal, the worker must physically acknowledge it by raising one hand above their head. These human regulations are integral, non-negotiable components of the station's localized safety algorithm. The human body is treated as the final, most vulnerable variable in the railway's operational matrix, requiring the strictest compliance. Shifting perspective from the trackside up to the station manager reveals the scale of this system. The station manager acts as a local computing node. They enforce the PKS to translate centralized dispatch orders into safe physical reality on their platforms. Zooming out to the entire national railway infrastructure shows an interconnected web of these localized algorithms. The safety of a high-speed intercity train relies entirely on its ability to pass safely through these interlocking localized jurisdictions. National network safety is the emergent property of decentralized, fiercely protected local algorithms. Standardizing the physical world of a railway is a battle against geography and physics that cannot be won. KTMB solves this through the strict administrative lifecycle of the station working order, tailoring the rules to the shape of the terrain. By controlling signal translations and trackside behavior, localized chaos is contained. This invisible layer of localized procedural code forms the actual architecture of a zero-fail network.